Good morning, respected members. Now we are going to start the first progress presentation of Rupjyoti. All the members already joined. Only our best sir, he may be somewhere. He is joining shortly. So Rupjyoti, you can start now. Please start.
So, good afternoon, respected panel members, scientists from different organizations, and my respected Dean sir. So, this is my first progress report under this project PhD work. My research title is AI-driven framework for real-time monitoring of nutrient deficiency in rice using leaf image analysis. So I have already completed a few works in the previous semesters, and now I'm this whole progress work is conducted under the guidance of Dr. Bora sir, Dean School of Computing Sciences. So first, I want to recap the objectives of this PhD research work. So the first objective was to perform a comparative study of image denoising and enhancement techniques, and hence to design and implement an adaptive image preprocessing and enhancement pipeline suitable for preprocessing rice leaf images captured under field conditions. So the first part of this objective to perform a comparative study of image denoising and enhancement technique was already completed in previous semester. So now we are working on the second part of the objective one, and the second objective was to develop, evaluate, and fine-tune deep learning models for accurate classification and prediction of rice nutrient levels, especially nitrogen, phosphorus, and potassium using annotated rice leaf images. And the third objective was to develop a lightweight and user-accessible prototype system for real-time rice nutrient monitoring and fertilizer recommendation using AI models. So in previous semesters, I have completed the critical review of rice nutrition monitoring using AI-based techniques. I have already studied the works done by different researchers regarding this area. So, and the review work was presented in ICCIT 2024, organized by British University of Vietnam, and also published a paper. The abstract was published the paper was published in Innovation and Challenges in Computing Games and Data Sciences, published by ICIJ Global in the year 2025. And the second, we have conducted a comparative study of image denoising and enhancement techniques for pre-processing digital images of rice leaves. So for this study, we have used the images available in public domain in Kaggle, and we have simulated noise like Gaussian, saltpeter, and speckle and random. So hello. So also we have used the common image filters for denoising the images, and like mean, Gaussian, median, bilateral, BM3D, and BM3D filters. And then after that, we have used the contrast limited adapted histogram calculation technique for image enhancement. And these are the results we have, which I have already presented in the previous semester. But for just for as the current work is related to the previous work, therefore I'm just showing some slides of the previous work. So here the results are here. So image with Gaussian noise. So we have seen that different. Overall, we have seen that for different types of noise, different types of filters is required. So there is no common solution for all the noises. So uh, so these are the findings. So the key findings are there here. So when bilateral or BMTT denoising combined with Klehe with tile size 0.5 and clip limit 0.5 and tile size 5 by 5. So apply images containing Gaussian noise. The resulting images showed the clearest leaf structures and highest contrast. And solvent paper noise is best removed using median filter. Veins and lesions boundaries may be brought out afterward by applying the Klehe, again 0.5 clip limit and 5 by 5 tile size. And BM3D reproduces persistence speckle to lowest degree. Meanwhile, a bilateral filter more effectively preserve fine edges depending on one's priority for noise suppression or edge detail. So, in the previous, we have seen that different types of noise, uh, we have to apply different types of filters with different tuning. Also, different tuning is also required for different parameter tuning is required for different types of noise. So we have uh, this review work. The comparative study work we have presented in the conference, international conference on data-driven AI, organized by the Assam Kazima University, Jorhat, and it's the best paper award. And the abstract was also published in data-driven AI abstract book, and also the paper was published in International Journal of Agricultural and Natural Sciences on September 2025. So here we have the traditional method of image pre-processing or image denoising. We have seen some problems. The traditional denoising techniques often struggle with preserving image details, adapting to diverse noise types, and generalizing to real-world conditions. So actually, so for this problem, we have gone through some processes or from taking help from some deep learning methods to first estimate the noise. Here, our concept is to estimate the noise first. That what type of noise is there, and what is the level of noise in the let's say in the image. Then we have used another model to denoise this noise. So we have introduced one architecture. So this is NEED need architecture for pre-processing images. So in this need architecture, we have the noisy image and the one noise estimator model is there. So that noise estimator model will estimate the type of noise, what type of noise is in the noisy image, and also the level of noise in the noisy image. So that output from the noise estimator model will be provided to the expert denoiser model. So the expert denoiser model will take three inputs. One is the noisy image, the second one is the noise type, and third one is the noise level. So in noisy image, which two metadata will provide to the expert denoiser model, and that denoiser model will uh, denoise based on the condition, what type of noise is there and what amount of noise is there. So based on that condition, the expert denoiser will denoise the image. So basically, the pre-processing step is very important because we are going to deal with the farmers. Then farmers do not have the sophisticated mobile phones or sophisticated camera with them. So they will capture with their smartphones, budget smartphones with limited megapixel camera, so on, and in field conditions. So must have some kind of noise. So we cannot directly process or then directly supplied to the classification model to identify whether it is nutrition deficient or not, because that will definitely provide us some errors or some kind of inaccuracy. So therefore, we have planned this model. So before providing this image input to the directly to the classification model, we will process with these two models. First, we will estimate the noise, then expert denoiser, or you can say conditional denoiser. We named it expert denoiser because the term will be better to spell like NED, the need. That means we have the need to pre-process the image so that we can get a quality output, or you can say accurate output. So we model name this model as need, NEED. So in first, let us go through the noise estimator model. So the architecture of the noise estimator model. So we have the input image, RGB image of size 256 by 256 by 3. So and here we have initially for suppose for training we have some publicly available rice leaf images. So because as we are going to classify or study on rice leaf images, so we are completed the pre-processing task also with the rice leaf images. So we have 5,000 rice leaf image data. So we have they are of different sizes. So we have standardized the size into 256 by 256 by 253 RGB channel. So and then we have convolution layers. So to extract the features like edges, textures, and complex patterns. Then pooling layers are there, reduce spatial dimensions, retain essential features, and global average pooling there. So which compresses feature maps into vector, and the finally the dense layer, the large abstract representation, and the two outputs. Uh, the noise estimator will finally classify into two outputs. One is the noise type, and another is noise level. So in noise type, we have initially we have four classes: the Gaussian, random, salt and pepper, and uh, Gaussian, random, salt and pepper, and speckle. So four noise types are there, and three levels of noise: low, medium, and high. So those are the outputs from the noise estimator, and this output will be treated as input for the next model, that is expert denoiser model. So how we train? These are the steps how we train the model. So image loaded, we have loaded 5,000 images from publicly available domain, and then step two, we have resized the image to uniform size for a consistent input shape. And then step three is the noise synthesis. We have synthesized different types of noise, as I have mentioned. The four types of noise we have synthesized to the standardized data set. That is salt, pepper, Gaussian, random, and speckle, and varied noise levels, low, medium, and high. Then we have the level image, each image with uh, noise type and noise level. Again, we have split it the data set for training and testing, so 80 by 20. Then we have trained the model with 80 epochs and with batch size 32. So this is the actual model structure. So these are training data. So as we can see that as the epoch increases, the number the loss decreases, and again uh, this is noise type loss, noise level loss, and these two are accuracy. So we can see that the accuracy, noise type accuracy, and noise level accuracy increases as the number of epochs increases. So the noise estimator, the performance of the noise estimator model. So precision 94.76, recall 94.7 for noise type, and F1 score 94.69. And for noise level, precision is 99.07. This is, I think it's near about near 100. So recall 99.06 and F1 99.06. And this is the confusion matrix. So we have used 5,000 images. So you can say for especially for salt and pepper noise, it is 100%. It is showing 100% accuracy. So you will see the final outputs where the salt and pepper noise is there. The model will extremely removes the salt and pepper noise. So the final output I'll show it. So this is the ROC curve. So here, as I've told that in SNP, the salt and pepper noise, we have seen that it provides 100% accuracy. That is, all the salt and pepper noises are detected by the noise estimator. And Gaussian is also 7.18. Yes, Gaussian for Gaussian also 97.18 and 90 random 92.44 and speckle even 98.95 is I think it's better. The maximum times we encounter Gaussian and random Gaussian random speckle. So for these noises we have one it's near about 90 and for salt pepper and Gaussian it's like near about 100%. And noise level prediction accuracy here, low noises are detected 100%. All noises are detected, and for medium, 97.51, and for high, it is very easy to detect the high noises. So here it is near about 100, 99.58. So overall noise prediction is 94.7%, and noise type prediction and noise level prediction is 99.06 as we have seen in the previous slide also. And the combination of noise type and level combined, if we have synthesized Gaussian plus low, so it is again predicting also Gaussian plus noise. That pair in a pair, type and pair, so it is also better because sometimes it happens that we have introduced random noise with medium, but it is showing random low. But no, it is showing 93.98 cases, 98% cases. We have seen that they are predicting with same pair. If it is Gaussian low, it is predicting Gaussian low, not Gaussian high or random high. So like that, we have seen that the noise estimator is working very excellently. And so next we have the expert denoiser model. So as it's a very resource, actually the denoiser model actually takes a heavy resource. So we have tried two models, one model with 46 layers and another model is 120 layers. So in the lower, we named it as light model, expert denoiser light model, and another as expert denoiser uh, uh, deep model. So, so this structure I put it horizontally because it is not possible to show this model here. So, so I have written this features here. So the key feature is the feature-wise linear modulation conditioning. So this will adapts filters based on noise metadata. So the noise metadata we have provided from the noise estimator. So it will work based on those data, and residual learning predicts noise instead of clean image directly. So we have also tried another model which I am not presenting here because I discarded that model, one unit model, which will directly predict the clean image. But here, this model will predict the noise from the image, and then it will subtract the noise from the noisy image, and we will get the clean image. So that is the concept. But some here you can see the next model. So some problems are there if we use this model. This model is fine, but have some problems like sometimes this model creates some artificial improvement. You can say looks better because you can see the data, the structural changes. Both the model have the ability to maintain or increase the structure of the original image. Suppose if you compare with the clean image or the original image, it will increase the SSIM or structure will increase, but as it incorporates some additional informations. So the PSNR decreases in decreases means in some percentage of data. So so this is the training line. So as it's the regression model where just showing only the training. You can see while this increases, the loss decreases. So as it is not a classification model, we are not showing here the other figures like precision and other things. So the combination, the result of the combination of the noise estimator plus expert denoiser model light. So here the graph is not visible. Na? So the first one is yeah. So the first is the average PSNR of noisy and denoised image. So uh, here you can see the PSNR increases. The orange line is the PSNR of the denoised image, and the blue line is the PSNR of the noisy image. And here the SSIM. So SSIM increases to near about, it is near about 1. So PSNR increases, and this is the PSNR of the noisy image. So here is the data. So we have seen that PSNR increase in 3192 samples, that is 63.84%, and decrease in 1807 number, that is 36.14%, and one sample remain the same. So average increase in PSNR is 10.3. If these are the you have predicted noise or cleaned noise from 5,000 images. So among 5,000 images, 3192 samples in case of 62.84%, the PSNR increased. And if we say overall average of the PSNR of the all the images, so it is increased by 10.33%. Suppose if it is 30 initially, then it increases to around 33. So this is the PSNR increase. So overall increases, but if we see as per the sample, yes sir.
More by yes.
Okay, then SSIM increase in 4420 samples, that is 88.4% sample. In case of 84.4% samples, the SSIM increased, and in 269 samples, it is decreased, and 311 in case of 311 samples, it remained the same. And average increase in SSIM is 42.50. That is structural. If you can say the structural increase is highest. That means as you will see the previews of the images, then you can also observe that. So here the observations are from the noise estimator, sorry, expert denoiser light model. So the model is effective in most cases, but not universally. Some noise type or levels may be harder to handle, leading to PSNR drops. Even when PSNR drops, SRM often improves. This suggests the model prioritizes structural and perceptual quality over exact pixel matching. And actually, that is important for us for further classification. Actually, this is the main point because structural improvement is required for classification model. So PSNR you can consider you can compromise with the PSNR, but structure SSIM is important. So this model actually the output of the model is better. So these are the real samples. So the first one is the clean image, second is the noisy image, and finally one is the denoised image with the full model. The here the noisy image is supplied to the noise estimator, which will provide you the noise type and noise level, and that output will be treated as input for the expert denoiser model, and this is the output. So here you can see in case of this sample, so the PSNR is here done in case of noisy image. The PSNR is 23.59, SSIM is 0.74, and the denoise image we have 34.97 in PSNR, and SSIM is 0.99. So very I have also mentioned that the salt and paper noise. So here we have the originality, it has SNP and low type of noise. And also the system our model predicted salt and pepper noise with low intensity, and also the model denoise the image with a great extent. So the second image we have, this is the second image. So here PSNR decreases. So you can see PSNR is 40.01, and then the denoise PSNR is 33.69. But SSIM, the noisy image SSIM is 0.94, and the denoise image is 0.97 SSIM. And here also the prediction is correct, Gaussian low and Gaussian low. So these are the samples. So the next one is the expert denoiser deep model. So here we have increased the film layer. So we have in the previous case we have 4 iterations of the film layer, and there also we have 4 iterations of a residual block where the film layer is applied to alternative blocks. So here in each block we have used the film layer, and total 8 residual blocks are there. So the number of layers increased to 120, but the performance, so it is actually some you can say the concept is same for both the models, but the number of layers is increased. So here the deep residual stack we have 8 blocks, and in the previous one we have 4 blocks, and among the 4 blocks we have used only 2 film layers. Here we have 8 residual blocks, and for each layer we are using the film layer, so which will generalize the output. So we have lost some information in the previous model. So here it will tries to keep more information in to the final output. So again, both cases, I have to also mention that initially we have tried this model with MAE as a loss. So, but that provides some kind of errors or inaccuracy. So we have introduced the hybrid loss, where we have used MAE and SSIM both as a loss function. So this that will improve the overall performance of the model. So that is one of the key point of the both the models. So here also this is the training graph. So where we have depicted the loss. So again, this is PSNR. The first one is the PSNR of noisy and denoise images, PSNR comparison. The second one is the SSIM comparison, and in both the graphs we have seen that PSNR and SSIM increases. So here is the difference. So in first case we have seen that 63.84% increase in the PSNR, and here this model provides 71.12 increase in PSNR, and again SSIM is increased in the previous one 88.40, and this deep model provides 92.90% increase in the SSIM, and again the average increase in PSNR is 19.79, so which is double the previous one. In the previous one it was 10.3, and here it is 19.79, and again SSIM, in case of SSIM it was near about that in previous case 42 point something, and here it is 44.41, because both the models provides good SSIM, but there is a difference in the PSNR only. So if we compare the time required for predicting or processing these images, so the deep light model takes 79 seconds for processing, I can say 5,000 images, and this model takes 99 seconds for processing 5,000 images. The 20 seconds are different in 5,000 images, which is very less, and I will so later on, there is a difference of 4 milliseconds in both the models. This is a heavy model, but it requires more time for training purpose. But for prediction, both the models takes approx same. The difference is only 4 millisecond per image, so which is very less. So, this is the performance of the second model. So here, so is it visible or not? So here also salt and pepper high, but the prediction you can see the improvement. So that it is near about the clean image. So the SNP noise is totally removed, and the structural improvement is there. So here you can see 0.16 SSM is 0.16, and the final denoise image has 0.97. So it's far better. Then this is here also 0.7 SSIM and 0.9 the denoise image. PSNR is 31, and the denoise image 35.17. Again, salt and pepper. So here I have already told that in case of salt and pepper, it 100%, and the image, the sample image also detailed this. So these are the samples. So here the comparison between these two models. So this deep model has stronger feature extraction. So as I've already explained it, here we have the increased the residual blocks to 8 blocks instead of 4 blocks in the light model. So this improves captures more complex noise and subtle structures, and better at handling high level correlation in images. This texture fine details remain same. Then consistent film conditioning. So in the deeper model, film is applied in every residual block, not just selectively. Or you can, I have already mentioned that residual film layer is applied alternatively in the previous model. Here we are using in each residual block. So this means the metadata influences the network more thoroughly, leading to better adoption across diverse noise conditions. And the multi-scale processing steps is there. So here, in the DIPOM model, we have used downsampling and upsampling. So downsampling captures the global context like large noise structures, and upsampling restores the fine details, and skip connection merges the both, so balances local detail and global structure. So advantage handles both fine grained noise and large scale distortion. So like we have seen that in random noise we have around 93 point. So this thing it will improve. So then high representation capacity and improve perceptually. We have seen that SSIM is increased. There we have 42% increase in the SSIM. Here we have 44%, and also in PSNR. So we have already discussed the data. So the final observation. So here, in case of lighter denoiser, is lower complexity and faster training. So achieve moderate around 64% increase in PSNR and SSIM 88%, and advantage for resource constrained environments or quick deployment. And deeper denoiser, higher complexity and slower training, so need some more time for training. So we have tested in our server where the lighter model takes around 4 hours to train with the 5000 dataset. So, and deeper denoiser requires around 6 to 7 hours to train. So I have already mentioned that only the training time difference in the training time, not in the prediction time. So prediction time we have already here stated here. So 90.8 millisecond required by the deeper model to denoise an image, and 15.8 millisecond by the lighter one. That is some difference with a difference of 4 milliseconds. So this is very less. So I think we can go for the deeper model because it's accuracy or prediction level is high. So we'll definitely go for the deeper model. So other activities during the last semester I participated in an online Tall AICT FDP on real world AI and ML. So it is organized by Assam Skill University in the month of November, and another FTP organized by Kaziranga University. So this one was offline. So in the same month, 10th of November to 15th of November. So these are the works that I have performed, and these are the works to be performed. So we have to design a model to process the output from this need model, that is the classification model. So we'll develop the deep learning or CNN-based classification model to detect nutrition deficiency in rice plants through rice leaf image analysis. Then after that, we'll collect some real-time annotated rice leaf image dataset, collect data, and create a new dataset in the next rice season, and train the model with the real field data. And after that, we'll develop a lightweight and user accessible prototype system for real-time rice nutrient monitoring and fertilizer recommendation using these AI models. So these are the works I have done till now and to be done is presented here. So if any suggestion or questions are there from the respective members of the panel, so I'd like to welcome. Thank you.
Thank you, Rupjyoti sir. So in the coming semester, we have a plan to get the real data set. Right? If everything goes well, then we will minimize meetings. Just what's needed. Now it is physical. I think I am audible now. So this coming semester, we have a plan to get the real data. And for that, we have some plans. And if everything goes well, then revisitors will get the data. And in this case, we should have some expertise knowledge with us. Like Bhavesh sir can also help for that part, right? For that real means data set collection. And Rubul sir is always there to help the suggestions that we need in the computer visions. So, respected members, if you have any comments or suggestion, please put forward.
Dr. Dibya, Happy New Year.
On sound.
Am I audible? Hello.
Yes, sir. You are audible,
Yes,
sir.
sir, you are audible.
Yeah. So, Rupjyoti, the presently whatever the data set you have used, it is you have collected from where? Hello. Rupjyoti Chutia. Am I audible?
You are audible, sir, but I think they have missed the connection. But
Oh, okay.
I'm hearing you,
Yeah,
sir.
yeah. I think they are not in the line.
Now we can hear you, sir.
Okay.
My point was that the data set, whatever presently you are using, you have collected from which data source?
Actually, sir, for initial pre-processing task, I have taken the data from Kaggle. Actually, two data sets are there. One
Okay.
is the one is the NPK deficiency data set, and another is the disease data set used for disease detection. The both samples are both have the samples of rice leaf images. So we have taken these images, right sleeve images, as input for our pre-processing tasks, sir.
So, what is the number of sample size of the data?
Sir, actually, for training, we are using 5,000 data, but we have
5,000.
7,500 data. We are using only 5,000 for this purpose, actually, sir.
Okay. So, have you compared your model with the recent models? Actually, I somehow missed your presentation in between.
Yes, sir. Actually, sir, we have done a comparison in that with the traditional models, traditional actual way of denoising the images. So the traditional way was to denoise with the different types of filters, and then for image enhancement, we have used contrast limited adaptive histogram equalization, that is with clip limit 0.5 and tile size 5 by 5. So that's our previous work, which was already published, and in that work we have seen that actually for different types of noises or different levels of noises, we have to treat them differently. So if we use the common practice of removing noise, or we have studied different papers or research work. So there they have applied some kind of linear or nonlinear filters first, and then use different techniques for image enhancement. So this is something like in agriculture say it as a blanket dose. So if there is no requirement of fertilizer, we are providing fertilizer. So that is called actual blanket dose. Professor definitely know it. So if we apply the same type of filter and same type of image enhancement technique for each type of image, definitely that will deteriorate or degrade the quality of the image. So we have planned to actually design a model, so which will first estimate the noise, estimate the type of noise, what type of noise is there, and what what is the level of the noise. So noise estimator models will first estimate the noise type and noise level. So then it will provide the output to another model, that is the expert denoiser. So we named it as NEED. I think if you miss it, sir,
yes. NEED, yeah, need.
NEED. So NEED is noise estimator and expert denoiser. So we have named it a need. So the noise estimator will provide the noise type and level of the image, and the expert denoiser will take three inputs. One is the noise image, the second is the noise type, and the noise level. So three parameters will be provided to the expert denoiser, and based on that input, this will actually predict the clean image. So actually we have designed two models, expert denoiser model. One is light with 46 layers, and another is deep with 120 layers, to actually to increase the PSNR level or the image quality. We have introduced the second deep model, because the first model have some actually some kind of loss in the PSNR, but increase in SSIM. But the final deep model has, we have both the PSNR and SIM increased. Basically, the SSIM is required, the main factor for classification. Still, we have designed this model, and the performance of both the models are good, but the second model performs better, sir. So we have taken the second model, that is deep model. So, and it is also efficient in case of, you can say, the time, for as we are planning to design a real-time I can say nutrient deficiency model. So nutrient deficiency classification model. So here the pre-processing task, it takes very less amount of time. So we have compared also compared the time of both the models. So for denoising the 5,000 images, the first lighter model takes 79 seconds, and for denoising 5,000 images, the second, the deeper model takes 99 seconds. That is average you can say 19.8 millisecond per image for the deeper model and 15.8 millisecond for the lighter model. There is
Lighter model.
a difference of 4 milliseconds only. So you can, if you suggest or if the panel member suggests, we can go with the deeper model.
Deeper model, yeah.
Yes, sir. Yes, sir.
No, now what you can do is that because recently also several deep learning based noise models also came, na? So at least 2-3 models you can do some comparison.
Oh,
So,
okay.
before sending it to some journal or your work.
Okay.
Some kind of comparative study should be there.
Okay. So we can also include the traditional method also for comparison with this or not, sir?
Yeah. Traditional one will work, but along with that, deep learning based model also, because your model is based on the deep learning based technique, right?
Yes, sir.
So with respect to that, at least recent 2-3 models, if you can compare, then it will be justifiable, na?
Okay, sir.
So in the meantime, you can have a look on that.
Yes.
Yeah.
Okay.
Okay, from my end. Yeah.
Okay, sir. Thank you.
All
Yeah.
right.
That's a very good suggestion from Rubul sir. So we'll include 3 other models and compare with ours in the coming sessions. Okay. So 2 works, 1 this one, along with the real-time dataset collection. Any other suggestion from the members?
No, sir, it's okay from my side, sir.
Okay, thank you, sir. In the coming sem, we will need your expertise knowledge. I think already Rupjyoti sir discussed with you about our planning, right? That rice field. So there we will need your knowledge, means expertise knowledge on that, so that we can have our own real-time data set. And we will go for means implementing the model with reference to that data set. That's our planning for the next semester.
सर म्यूट है आपका.
Oh, is it okay?
Yes, now it's okay.
Okay. So that's our plan. If all the members agreed, then we have already noted down your suggestions. And any other comments, please put forward.
Okay, sir. Am I audible, sir? Hello, am I audible, sir?
Yes.
Okay, sir. I'm sorry. First of all, I'm sorry because all of a sudden, sir, our VC sir called me. So
No,
that
no
is why I
problem,
went there. So, and whatever I have seen, he have presented very nicely. And so far as the this progress is very satisfactory, I think so. And accordingly, what the Bunia sir suggested is that the traditional that method, yes, we will have to take that method also because for comparison and all, whatever the present models were there. So, and in the coming days also, I think so. It will be going in the right direction. It will be going in the right direction. And Rupjyoti, you can come at any time to me for that consultation and all. We always used to be in contact. So you can come to me personally. You can come to me in my office also. We can talk regarding the progress of that rest of the works. So
Okay, sir.
till now it is satisfactory. I think so. It's going on very nicely, and we are means expecting that within time this everything it will be completed very nicely. Thank you, sir. Thank you very much, sir.
Thank you very much, Bobby, sir. So we come to the end of the presentation. Respected members, we will need your digital signatures, and Rupjyoti sir will share one form with you, or you can share the signature. He can put there, and it will be sent to you, all of you, as a process of the University. So with this, we are going to conclude the meeting. Thank you very much, all the members, for your valuable suggestions and your time. Time to time, we'll need your suggestion. Apart from the formal meetings, we may also need your suggestion in the anywhere, any time of the semester. So Rupjyoti will be in touch with all the members. Thank you.
Okay,
Yes,
thank
sir.
you.
Thank you very much, sir.
All right.
Thank you.
Okay. Good day.